Okay, so we have assignment 8 released for you. And what we ask is that we need to implement the permutation encoded GA. Once you finish the permutation encoded GA, actually you can use that to solve the famous TSP problem. But efficiency-wise, it's not very well, okay? But anyway, for some automation problem, definitely we will have so-called sequencing in the problem. So in that case, you can use permutation GA to solve the problem. So, but again, since we are dealing with the job assignment problem right now, right? So in the previous assignment, we used binary GA to solve the job assignment problem. It is not efficient, right? Because we model that as a 0-1 variable. And if we solve that problem using the 0-1 binary variable, so we will incur a lot of constraint equation, right? So, but in previous assignments, that just let you get some exercise in using the meta-heuristic algorithm. We don't care about how many hard constraints or how many soft constraints are embedded with the problem. We can always use so-called penalty method to model that problem. So that is the merit of our meta-heuristic algorithm. We can solve all kind of problems, no matter whether there is a constraint equation or not. And does not matter whether that constraint equation is linear or non-linear or probably logical-wise even else. That kind of constraint, we can always deal with that, right? So that is the beauty of meta-heuristic algorithm. But the problem is that you need to carefully specify the objective value evaluation function. In particular, as you can see in your objective evaluation function, you need to decode it, right? Decode the solution generated by the GA. Decode that into your solution or your problem, and then evaluate the objective value for that solution, for that encoded GA, and then send it back to the GA. So the only interfacing function is that objective function between your problems and the GA solver. So that is the beauty of our tool. So later on, if you bump into any automation problem, try to use your GA to solve that. But you need to model the problem using a particular type of encoded scheme, right? So for the job assignment problem, definitely we can use the either way, it's binary GA or this one, permutation encoded GA. If you use permutation encoded GA, definitely you will not have any constraint equation generated anymore. And you can directly use, if that is the A job problem, we simply declare that the permutation GA, the number of variables is 8. And it's so rapidly, so consistent with the problem was. So definitely, if you finish the permutation GA and you can compare the solution generated from the permutation GA with that in the binary GA, you will definitely appreciate if you have a permutation GA, you can solve job assignment problem readily and directly. So you will get a better solution than that. Okay, so in assignment A, I think you can start from your previous solution. That should be previous assignment 7, right? So, but here I'm not going to. You should do that by yourself. Okay, so probably the best way probably, if you prefer, I mean, using the your user interface. Developed in assignment 7, and definitely you need to migrate your assignment 7 into assignment 8. Okay, so by doing the same trick we conducted before, right? So you can copy assignment 7 into a new assignment 8, and then make a necessary modification about the namespace and the solution folder name, project folder name, and probably you need to modify some contents in the solution file. So I will ask you to do that by yourself. What I'm going to show you is that, well, we will increase a new derived class in your library. So later on, you can move your library to any, you can deliver your library to other users. Okay, if the user familiar with the C# programming language, and then the user can use your library to solve their problem. Okay, that is the idea. So because let me. In here, I'm still using the assignment 7. Okay, so since right now we have defined a good skeleton, I mean, for the genetic genome, right? So it will be very easy to extend our library to incorporate the encoded permutation encoded GA. So back to your GA library. Right now we have binary GA. So permutation encoded GA should be almost similar to the binary GA right now, but for each different different encoded GA, they should have their own categorization about the operator, right? So as you can see, in your binary GA, we have a binary crossover operator. We have 1-point card, 2-point card, n-point card. But remember that even though we are dealing with the permutation GA, the cut points, as you can see from the slide, it's traditionally always has 2-point cut. But you need to think about that. Probably in your problem, the problem dimension is large, quite large. Probably the number of chromosomes might be higher than 1,000, right? So in that case, if it's just a 2-point cut, the efficiency, the solution will not be, not be good enough. Okay, just like what I have demoed in the video tab for that simple problem. If the number of variable is quite large, then 2-point cut will not generate versatile children at all. So in that case, you need to provide n-point cut for that. But right now, in the slide, what we are really dealing with 2-point cut, simply put, just like the example in the quiz. So if you are capable, you should let the user specify the number of cuts. And properly, you should determine it by yourself. So you know the number of variable, right? Number of gene, right? So you will determine the number of cuts by yourself. But you need to carefully design the logic. So what I'm asking you is that you need to hand in the pseudocode first. I mean, for example, in the permutation GS, you can see from the slide, at least we will have 5 different kinds, probably 6 or 5, I cannot remember exactly. So in the slide, we provide one, right here. In the slide, we provide 2, 4, 6. We have provided 6 canonical crossover operator, right? So I'm asking you, try your best, try to implement as many crossover operator as possible. So the score will based on how many you create, and you need to carefully debug your code because it is likely to generate the wrong children chromosome. Probably you will see where certain kind of number has appeared more than once in your children chromosome. So it is easily to generate a wrong answer. So you need to carefully debug your code. So one I'm asking in this assignment, you need to submit the pseudocode for each implemented crossover. And here I kind of provide you a it seems very complicated pseudocode, right? But later I will show you. I will show you. I mean, step by step to see what this pseudocode is doing. I mean, basically this pseudocode is for implementing a PMX crossover operator. Okay, so if you implement any one of these crossover, you need to prepare pseudocode first. So in preparing the pseudocode, you start thinking about what kind of extra data is related to the data structure you need in order to carry out this kind of operation. All right. So again, if in your permutation GA, if you want to do certain kind of operation and you need some scrap variable to carry out certain kind of computation, make sure you allocate memory only once outside that function. That means in your object, just once. Okay. All right. So basically, you need to do is that in your library, so we add another class. So we will add a new class. So similarly, since I have binary binary GA, well, I might call it permutation GA. Yeah, I do not have a solver, binary GA solver. So you can use your own naming convention for yourself, but definitely the name should be a noun, right? So don't put a verb there. So permutation GA, fine. So permutation or permutation GA solver is totally up to you. So we have, and since right now we are developing a library which can be sold to your customers. So we like to specialize public. So then the outside world can instantiate an object or derive any class from your class in your class library. So inherit from where? From generic GA solver, from generic GA solver. So definitely you need special type. As you know, permutation GA is a integer, right? So it's specialized integer. The type is an integer. Okay. So once you declare a class inherit from generic GA solver, and you have not supplied any construct in this moment, right? But the parent class requires certain kind of constructor. So you will see red query came out. Okay, take a look at this the reason. So this video will show you what. We did not provide any corresponding constructor, right? So because the parent class needed this kind of variable, number or variable, optimization type, and objective function, and a panel, right? Okay, right? So we will prepare a constructor, and probably you can refer to the constructor of the generic GA solver quickly, and then copy from there. It will be much better, much quicker for you, right? So this is the generic GA solver. So let's copy it back to our implementation GA. So we need to provide number, well, this part, right? So parent ask this kind of parameter, but we need to get this parameter from children's constructor and then pass that to parent to invoke the constructor of parents. That is what I did. Okay. And here, because right now objective function we definitely know right now the type should be what? Should be the integer. This is delegate, right? It's a delegate. So right now, user need to provide a function complying with this delegate objective function. Right now, the type is int. Panel is not recognized. Fine. We let the Visual Studio edit that for us using system.windows.form. So by default, it's none. By default, it's none. So we're not going to provide any visual display. So we invoke the base. You copy this list, put in there. But what we need to pass to the parent constructor is simply the parameter name. I'm not going. It's not related to the definition, so it's okay. So, well, you can check the binary GA, the constructor binary. Oops. Okay. So we have this, well, a little bit complicated constructor, right? But if you look into the binary GA, the same thing shouldn't happen there. Binary GA, right? So number of variable, operation type, objective function, but in that case, it's a byte. And a panel. So probably I will add the initial, if the user can omit this parameter, if the user does not want any visual display. So they don't need to provide this panel. So by default, it's that. Okay, so similar, right? And in here, if later on you want to add another different kind of encoded GA, for example, real number GA. So how will you do that? So let us quickly add that skeleton. So later on you can implement it by yourself. So suppose I add another class. This is not required in assignment 8, but I prefer telling you, well, probably in your direct class, the user might have an additional requirement. In that case, they can ask that requirement in the constructor. So for example, if it is a real number encoded GA, real number encoded GA. Again, a lot of automation problem is involving the real number. So in that case, you can use your real number encoded GA to solve that. So public, right? Real number encoded GA. Inherit, again, inherit from where? From generic GA. What is the type? Double. Okay, our data type is double. So similarly, decision happen again, right? So in this case, I will copy again binary permutation GA. So I kind of copy everything and then change the name. It will be more directly, right? So for real number encoded GA, well, I copy this constructor, paste here, and then change the construct name into this our class name. So right now I have a real number encoded GA. So similarly, maybe this should prepare this for us using. But objective function right now is what? Objective function should be double. The type should be a double. So it's double encoded, right? But if you think about a real number automation problem, usually for each variable, user might need to provide what? Needed to provide the lower bound. For each variable should have a lower bound and have an upper bound. So in this case, number of variable, other than number of variable, user need to provide extra information for real number encoded GA. Otherwise, the GA does not know how to initialize the initial value, right? You need to tell the GA, well, for this variable, the lower bound may be 0, upper bound is 5. Another variable, the lower bound is -5, probably 10. You need to provide such kind of information for the GA in order to randomly generate initial value for you. So that means we will have an extra data required for real number GA. So back to the class design concept. Well, what kind of information you need? Then we will need to have a double array, lower bound. It's an array, right? The range should depend on number of variables. So real number need this one lower bounds for all the variables, right? And also a real number. These are the upper bounds. These data are extra data required and solely for real number encoded GA only. Binary GA does not have this, and permutation GA does not have it. But real number encoded GA definitely will have this one. So similarly, if it is an integer encoded GA, again, a lower bound and upper bound are required for that kind of encoded GA. So what I'm saying is that, and where can you get the lower bound? Definitely, you need to ask the user provide that before create a real encoded GA, right? So we ask that probably number of variable, and then we ask for double array. Oops. DOUBLE. Upper bounds, right? We will start from lower bounds. Fine. Make a copy. This is lower bounds. Lower bounds, upper bound. Okay. So right now in your constructor, the variable name is exactly the same as your data member. So in this case, we need to use this dot lower bounds equal lower bounds. So simply get the references. So the caller should provide this double array there somewhere. I mean, I don't care. I just simply copy the reference of this array back to this data. So I'm not going to instantiate any variable. Okay, I'm not going to instantiate any memory for our robot. So the user need to simply pass in the reference, the starting address for that array to me. So then I can hook it up with this data member. So upper bound equal upper bound. Right. So constructor-wise, you should do this, and then make sure that, because right now we have green curly line, right? So because we need to do some documentation, so we should add some description there. I mean, for each public function, so use this tag comment to write something to help your user to invoke this constructor to create a real number equal to GA. All right, so let us back to the permutation GA. So right now we focus on our permutation GA. So similar to binary GA, right? So we will have a different kind of canonical cross operator to let the user select it, right? Oh, okay, so definitely I will have a new enum to be specified for our genetic solver. So purely focus on our genetic GS, our permutation encoded GA. Okay, so beside this class, we have add another public class. Not class, new permutation crossover operator. Permutation crossover operator. PMX is not good, okay, but so far fine. PMX, right? So look into the slide. PMX, OX will probably make it much more readable. So I will spell out the full name. PAR, partial rapid crossover. So I can use X stand for crossover. Otherwise, it will be very lengthy. Partial mapped crossover. Order crossover. Position based crossover. Order based crossover. Cycle crossover. Subtool exchange. Okay, so as many crossover you can implement, fine, just put it there. So similarly, what we will have, we will have a mutation operator, right? So again, add some comment to it. Canonical crossover operator. Canonical, the word means that standard， 或者是叫阳春的就是 canonical 标配canonical crossover operator. It can be used to deal with all kind of problem. Anyway, that's canonical means. And later, if you are doing certain kind of research, you can specifically design a crossover to deal with certain kind of problem. Okay, so in that case, that should be customized crossover operator anyway. So we are covered, and then it's not permutation crossover, mutation operator. So do it by yourself. Check it. Look into the slide, right? I think we probably have 5 or 4 different kind of mutation. Cannot remember exactly. This crossover, subtool, heuristic mutation, right? insertion, inversion, displacement, right? So at least we have a reciprocal exchange mutation. So again, we have a bunch of canonical mutation operator there. All right, so let's do GA, right? So definitely right now we have, so we will have what? Adding up some public property, right? So the name is crossover operator. And if you don't want to specify any data field, you can directly use capitalize or declare this property, right? And I put set and get there and do the initialization. So initially with PMX partially member crossover operate. So similarly, you will have a mutation prepared there. You will have a mutation operate, crossover operator, right? Well, inversion. So I put an inversion there. So you need to add the rest of them by yourself. So I mean, for a GS solver, so right now we have a crossover operator specified right now. So similarly, we have a mutation operator. Mutation operator. Set get. And we initialize it into inversion. This is the only one we have. Okay, so what else should we do? I mean, for our permutation GA? So definitely you need to perform crossover operator, right? So look into so let the Visual Studio help you overwrite. All right, so we need to prepare our own crossover a pair parent, right? And initialize population. Okay, so definitely we need to start from initialize population, and then mutate a parent with gene number based, right? So what we need to do is just override this function. So initialize population. So how can you initialize population? Well, you look into the example which has been done in binary GA. Initialize population. For R, start from 0 up to population size, right? So we need to specify that. All right. So override it. So copy it. Permutation GA right here, and then here. So how will you do that? So right now your chromosome is integer, permutated integer, right? So again, we have randomizer can do that, right? So how can you do it? So basically, we know the number of genes, right? So for each chromosome, right, C, chromosome should be equal C first. Which means initialization of 0, 1, 2, up to number of genes minus 1. It will not going to work, right? So we should ask that we need to shuffle this array, right? Shuffle this array. So once we assign this value, so definitely probably you don't need to specify that value. So probably you can just directly ask what? Remember that this we have a shuffle. I don't see it. So in generic GA solver, let me check that. Generic GA solver. Generic GA solver. So let me check about this function. So if you want to find a function, you can come here. That is generic GA solver classes right here. So how about the function? So far based on after. Shuffle an array. Oh, excuse me. Last time we declared as private, right? Oh, okay. Shuffle array. We did not declare that as public. So we're not going to set it as a repeat as private, but at least we have special productive. So protected. So we have shuffle array. Okay, and the number array. So well in here I can take the advantage of that function. Ask that shuffle for a shuffle array. So what is your array? Chromosome, right? The R chromosome. And how about a limit? Limit should be number of gene. Right? Or probably you can what? It's a number, it's a limit, right? Chromosome R. Oh, I'm sorry because last time is shuffle array is a byte, not byte array, not int array. So I'm sorry about that. So 举那个 GS over shuffle array int shuffle array. Oh, I made a mistake, right? I'm not going to do this. So I'm sorry. I just kind of made a mistake. This is the binary GA. So next to is okay. So it's resume. So let me go back to permutation GA right here. So I'm not going to set the chromosome here. Instead, I can directly invoke that shuffle an array, and I put chromosome. And I need to special limit the number of gene. Okay, so initialize population is just that simple. Okay, so it is done, right? But the most troublesome should be the crossover, right? So again, we override crossover at parent. So right now you need to pick up the gene from father and the mother, and then you need to put gene there from child 1, child 2 there, right? So, and again, you need to check about the specification about the crossover operator, right? So basically what you need to do is switch the crossover operator. Type, depending on the type, right? So case, first one, dot, partially map X. Right? Case. The second one, order X. Order X, order based X. So you need to implement one by one. And now, so I ask you guys, if you want to implement and crossover, you need to design the computational logic first, and then put it as a pseudocode, write it down as a pseudocode, and then submit it to me, submit it to the assignment. Okay, so prepare, submit the pseudocode in Word or PowerPoint or PDF file is okay. I mean, anyway, you need to design your computational logic. And what I'm here is that, well, I need to use square memory for me in order to carry out PMX. I might call it M array or map array. And the size of this array should be exactly equal to the number of gene. So don't, again, as I stated, don't use any new operator right here within this repeatedly called crossover function. So don't do that. But definitely, in order to carry out the PMX crossover, I need an array, right? So in that case, prepare that in your data member. So I will maybe call it int temp or whatever map. Map is dedicated for a partial map, right? So I might call it temp anyway, or probably just m. Fine. It's total object. Okay, let me put as m. And allocate the memory just once. Where? In our constructor, right? Since the constructor we know the number of variables, and definitely this square memory is just for the size is number of variables. So right here we allocate memory just one, m equal new int. The size is the number of variable. All right. So you have scrapbook memory for you to use. If you need another one, well, added is right here, especially array. Okay, so if you need any data structure to help you carry out this operation, don't invoke any new operator within this function. Just prepare that memory, prepare that data structure in advance, and then specify that as your data member, as your class member. Right. So if you carry out well, actually, since it's almost pseudocode, right? So I1 random number, I2 random number, wait, right? So you need to have a 2-point cut, right? So right now this algorithm is for 2-point cut. So again, right here, I might int I1 random number generate. So remember that we have inherit a randomizer. Next, one should be what? Number of genes, right? How about I2 randomize? Next, number of genes, right? And then since right now we need to proceed this crossover from the low press to upper press, so I need to make sure I1 is smaller than I2. So as you can see, if I1 greater than I2, swap I1 and I2. So here, since it's a pseudocode, I just say it. But in order to carry out this swap, you need to do that by yourself. Okay, so if I2, I1 greater than I2, how can you do that? Well, I need another one, right? So, but definitely it's okay. 10, right? So if this hash situation happen, I need to do 10 equal I1 equal swap, right? How can you swap both values? You need to have a certain temp variable to do that, to store the first value for you, right? I1 temp, excuse me. So that's swap. If you are good in computation logic, actually you don't need to have this temp. We can use exclusively O to do that, to do the swap. Oh, I never mind. Well, but definitely right now it's much easier for us to swap I1. So right now I1 is smaller than I2, right? So because it's a random number. But right now we make sure I1 is smaller than I2. So start from here. Okay, M1 array assigned to -1 for all I blah, 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 up to 0. Okay. We don't need to write it in using a for loop, but right here, I mean, since it's a mathematical expression, so you know what will be carried out for this line, right? So we look through every so right now in permutation partially mapped GA, well, for I start from 0, I up to number of gene, I plus map, I equal -1. So you design a logic to carry out this certain kind of crossover operator, and write down this pseudocode. And finally, the implementation-wise should be consistent with this pseudocode, right? So up to this point, okay. So right now we try to construct the map first. Okay, it's a little bit complicated, but later you will see what will happen. So right now we are about to construct this map, right? If take this as an example, we try to set up this kind of mapping. Right now we have an n always equal -1. So we start from this I1 up to I2. So as you can see, from I1 to up to. All right. So concept right here for I1 int I again equal I1 I up to I2 I plus. I still use index as I, right? So I plus. So I start from I1 to I2 -1. So I use smaller than I2. And then I check P1 parent 1 I equal parent 2. Then next it's a kind of format, means tell the reader that well this pseudocode the computational procedure is that well since I is an index, right, for the looping statement. So next I means that well just skip the rest of the code, right? So in C# programming, we should use continue, right? So right now, you know, if P1, P2 is continue, well, this suggestion is for this case. If it is 7, 7, then skip. It's done. There is no any mapping requirement for this pair, right? All right. So the first case for the first case is right here. If P1, which means parent 1, right? If parent 1, where is parent 1? Chromosome, right? Chromosome. Father is, excuse me. So notice that father is the index of the P1, mother is the index of the P2, C1, C2 for the children. So if chromosome father is exactly equal, excuse me, this one, I. So chromosome father is the chromosome, this is the gene. So P1I, P1I. So probably if you confused about the P1, because right now it seems that I have another index, right? So in that case, if you like, well, I can put a int array, right? P1 stand for what? Father. If you want to make your pseudocode consistent with your coding, fine. P1 is an array, right? P1 is an array. Chromosome father is an array. How about int P2 chromosome mother? So that will make your code consistent with pseudocode right here. If P1 I C I. All right. So if P1, well, the coding these are exactly the same algorithm. Either way, you use chromosome father or use P1, right? It's exactly equal P2 mother's I. Then next I continue. Excuse me. Okay. Okay, so you can follow that. Okay, similar follow that up. Okay. All right, I'm not going to write all the code for you. So what I'm suggesting is that try to follow this step. So for this part, we just try to set up a map stored in the M array. That's it. And then after that, I kind of start assign gene to the children. I start from 0, right, up to n-1. So if I is smaller than I, and then I smaller than I2, so within this crossover period and segment, right? So C1 take the gene from mother, P2, right? Child 2 take a gene from father. Otherwise, outside in both ends, we need to check the map. So sometimes C1 will pick up the mapped value from M. Sometimes trying to pick up from parent. Otherwise, probably you will directly pick up from the parent 1, parent 2. So in this algorithm, as you can see, we need to do so from I1 up to I2. So it's one pass. Within this one pass, we build up this memory map array. And then we need to take another pass. Start from zeros up to the last one. So this algorithm is kind of neat. We simply proceed to pass, complete this kind of crossover operation. So how can you come out this design? Well, you can think about how to solve this problem only by yourself. So you can construct this procedure only by yourself. So you can try different kind of way to do that. And probably you might need one or more than one array to store certain kind of object. Up to you. It's totally up to you. Once the result is correct, then that's fine. So I encourage you do your own logical planning in order to carry out PMX crossover. So let me. I'm not going to write the code for you, okay? So you can, if you want to implement the pseudocode I put in here, you can step by step doing that by yourself. What I'm going to show you, probably I use that example to trace you how I build this M array. What is that for, okay? So let me try to use this example to see what was really stored in this M array. So as you can see, initially, M array right here, 0, 0, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, right? So initially it's minus 1, minus 1, minus 1, minus 1, minus 1. Right here. So I can start from I1. Well, okay, can only do it. So start from I1 to I2, right? So I one by one minute. If P1 exists, then I1. So it is not the case, right? If n equal minus 1, and then parent 2 equal minus 1, which means that, so put the first pair, 3 equal minus 1, parent 3, right? You want mother, this father 3, right? Minus 1, and mother 2 is 1 minus 1. So which means that the mapping relationship between 2 and 3 has not been set up, right? Here 2 and 3, 2 and 3 and 2, right? So this is for the first case. If m current position is minus 1, for the mother is minus 1, then I do what? M this position, put P2's value there, and then put P1 value there. So in that case, 3 mapped to 2, right? So 3 mapped to 2. So I'm changing this value to 2. And then 2 changes to 3. So firstly, I do it this way. So for this case, it's met, right? So P2, P1. So right now, my main M keep this information, which is similar to your cases, 3 mapped to 2. All right, for the third part, 77, nothing happened. And then 1, 9 pair, 1, 9, right? It's 1, 9. So 1, 9, as you can see, 1 here is minus 1, 9. I'm sorry because, okay. Forget about that. So I will skip it a little bit. So I need to use 9 minus 1. So 3, 2, right? 3, 2. All right, 1, 9. So 1 is minus 1, 9 is also minus 1. So in that case, I put 1, 9, right? So put 1 into 9. And the m value to 9, and then the nice m should set up to 1. So again, I build up this relationship 1 and a 9, right? 3, 2, 7, 7, 1, 9. And then in that case, 2, 4. 2, 4, 2, 4, right? 2, 4. So 2 get into 2, it's not equal minus 1, right? It's not equal minus 1, right? But how about 4? 4 is minus 1. So this pair, one of these value in m is not equal minus 1, right? So in that case, so this shouldn't happen. If 2, 4, P2 is not equal, P2 is equal 5. So in this case is this one, P2 is minus 1, P2, 4 is minus 1. But the 2 is not equal minus 1. So this shouldn't happen. This shouldn't happen. So then in P2, I assign the value P1 value, MP1 value. Copy that to MP2 value. So I copy, okay, well, let me carefully choose that. So for 2, 4, 2, right? 4, 2. So in that case, because 4, 2, 4, 3. 4, 2. 4 and 2. So I copy the 3, 2 here. Copy 3, 2 here. 3, 2 here. And then 4, 2. And then 3, change that 3, 4 into 4. Then I do this work. So 2 does not matter anymore. So I copied from the 3 to this place, and then I have 3, right? 3, put a new comment 4 there. So which means that 2 and 4. So now as you can see, the most important is 3 and 4. 3 into 4, 4 and 3. And then 2 is, because right now it has been merged, so 2 is not important anymore. So I keep 4, 3 right here. So the next one is the 9 and 3, right? So you check a 9, it's not equal minus 1. And I think I have put, in this case, if this happened, and I assign another value, right? I think I have assigned minus 2. So that means this one turned out to be minus 2. Change that into minus 2. So which means that it's not important anymore. So the next one should be, is the pair is 9, 3, right? So 9, 3, you see 9, 3 is not equal minus 1. 3 is also not equal 1. So this should happen else. So in that case, where I put a minus 3 there. So we know right now we need to join both of them together. 9, 3, right? 9, 3, join it together. So the most important is that, so 9 and 3 and the 9, 3 and the 9, 3 and the 9 will be changed to minus 3, changed to minus 3. And check about the 1 equal 9 turned out to be 4. Turned out to be 4. So I put in here 1 change it to 4, and the 4 change it into 1. Anyway, I'm doing this kind of bookkeeping right here. Doing that. So eventually you will see that, well, 4 will map to 1, 4 will map to 1, and 1 will map to 4. And for the middle between 9 and 3 turned out to be minus 3 and a minus 3 there. So last one, 8, 5. Since 8, 5 are all minus 1, so change that to be 8 and 5. So after that, I have done this mapping. So I put the mapping information within this M array. It's an M array. So later on, I mean, if you cannot have an answer here, right? So last time we say that the final solution is 3, 7, 1, 2, 9, 8. Never mind, put it with 6, 5, 4. So we need to check out. So finally, should be 4 and 1, and then 4 and 1, and then 8 and 5. 8 and 5, the pair 1 and 9. So 6 remain there, right? So remember 5 turn out to be 8. As you can see, 5 turn out, if it is 5, change it into 8. If it is 5, change it to 8. If it is 6, 6 is minus 1, nothing changed. Since 6 is minus 1, nothing changed, so we don't change. But since 5, the map target is 8, so change that into 8. So it is changed into 8. How about the 4? If you take about 4, it should change into 1. So I put in 1 there. So similarly, this is 1, 8, 6. 1, check about the 1. 1 should change it into the 4. So change it into 4. 8 change it into 5. So change that 5. 6 minus 1 without any change. So that is the way I carry out PMX crossover. So I needed to construct this M array for the rest of operation. So we needed to check about the mapping target for the gene outside this crossover parts, right? So I mean, in child 1 per child 1 per child 2, so we need to do that. So this M helped me to do that. Okay, so you need to, well, in order to generate this pseudocode, you should prepare a data structure for you to carry out this operation. So what I have shown up right here is try to using this kind of temporary memory array for me to do the bookkeeping for the mapping information to store there. Okay, so I need to identify this situation, whether the new pair has already exist in 2 different kind of array, 2 different lists, or probably just simple one. So I need to identify this case. As you can see, during this pseudocode, I'm kind of identify this kind of situation, try to update the correct value of M. So after that, I can directly just go through this gene wise. So if within this part, I check the map. Otherwise, within this part, I simply copy from the mother to here, father put there. And after again, I need to check the memory again. So as you can see, the computation wise, I simply just use one pass. I can assign children's gene just within this one pass algorithm. Okay, so I will let you to do that. So at least you will have PMX pseudocode right here, so you can carry that out. Or probably you prefer your own algorithm to do the PMX crossover. Fine, try to design your own. All right. So if you need any extra memory to carry out the operation, remember that just prepare the memory outside this function. Just allocate memory once. Similarly here. Okay. So probably you might need another new array for you to help you do the mutation or crossover. So just pay attention to that. You prepare that memory, that means outside your function. So within this crossover operation, there should be no any new operator specified here. Otherwise, it will slow down your computational procedure. All right. So what you need to spend a little more time on designing all these computational logic. Okay. So at most we will have 6 canonical crossover operator, and then we might have 4 or 3. I cannot remember exactly the mutation operator. So you need to override crossover operator, and then for the override mutation wise, we will mutate a parent, right, with the gene to be mutated marked on this array, right? So we will override mutate a parent. So parent ID has been given to you, and you need to set up the gene value for this child, and then you need to refer this flag. And also we have a so-called population size based mutation, right? So override mutate a parent, the parent without any information about the gene. So you need to carry out by yourself. So basically right here you might switch mutation operator. Alright. Case. The first one should be inversion, right? Great. And if you keep adding up different kind of mutation, inversion, reverse. I don't know exactly, so you need to implement one by one there. So actually what we need to do is just override this stuff in this function only. Then later on you will use that to solve your job assignment problem. So if you can go back to your application right here. So similarly, I mean, initially we have binary GA, right? So we prepare objective evaluation function here. Job assignment problem objective function. So since this function is to be invoked with this binary GA, right? So binary GA will give you a solution in this format by the array. So right now, if you employ another GA solver called permutation GA, mutation GA. Okay, my GA solver, I'm calling it permute solver, right? Permute solver. So later on, you need to instantiate somewhere, right? When some button is clicked, but you need to prepare an objective function for this permutation GA. So let me provide a function. So this function is a very localized one. So that will be public, return double. So similarly, let me put it here. Permutation GA. So okay, let me move to here. So this is for binary GA. So we have permutation GA. So we should provide. Whether it is public, it does not matter. Once you have passed this function via dedicated, you will do that. So we will have a double job assignment problem. The name-wise is totally up to you. Encoded objectively function. So what do you expect you will get a permuted encoded solution from solution? INT array, right? So you know the length should be number of variable, number of gene. Okay, so return 0.0. So you need to do that by yourself. So basically what you need to do, you might have a double, right? You might have a double, which is array setup time, right? So we simply carry out, return that to it. So once you have this permute, excuse me, I did not deliver. Right, so we have permission GA here, there. So once you read in the problem, you have setup time there. So that will carry out something, solution. It probably will be very easy for int I equals 0, I smaller than number of variable, number of job. I mean, in your terminology right here, it's a number of job. So number of job, right? So number of job, right? And I plus. So setup time, total time. Start from 0, right? And the setup time should be total time plus equal setup time, right? Setup time. Setup time is the first argument should be job ID, right? And then to the machine ID. So right now, it's a number of job is machine ID I, and then the solution I is the machine is the job ID, right? Job ID assigned to the machine. So that's it. So it's very simple like that. So finally, is return total time. So it's so straightforward. I mean, because there is no any constraint equation. You don't need to specify any penalty at all. You just directly pick up your setup time. Solution I, gene I, right? Gene I, solution I. Gene I is the job ID assigned to machine I, right? So job, machine I. What kind of job has it been assigned to the machine I? In the solution I is the job ID. So job ID, machine ID, that's it. Setup time, accumulate all the setup time. So that is the objective value. It is about to be minimized, right? So how can you construct a constructor? So it's instantiate a binary GA, right? So similarly, if you have another button, or probably you have a new application, fine. So within this button, we create a permutation GA, right? So button 2. So permute solver, permutation GA solver, new permutation GA, right? So as you can see, number of job, right? So number of job, automation type, that minimization, minimize the setup time. How about objective function? As you can see, the delegate take int array, right? So remember that our function name is what? We prepare a function. Well, permutation encoded objective function. All right. Permutation encoded objective function. Okay, so the function type match that delegate, so it will there. And how about let me check about the signature of this constructor. So objective function and then panel. So you provide the panel. So okay, again, the panel which should be similar to this guy, right? So we provide panel 2, split panel 1, panel 2. So check about the check with the previous assignment. You were very similar to that. So you have a permutation GA solver, and then every execution button and then charting has been provided, so you can solve your problem. Probably you need to display your particular information somewhere, so you need to subscribe the event. So similarly, you can subscribe event right here, right? So you can, since right now permute solver object has been instantiated, so you can subscribe permute solver dot check about the event provided right now in your permutation GA solver. So update the initialization, when iteration complete, so what the business. Well, it's totally up to you. So that is the way we use our GA library to solve our problem. Okay, so that's it. I think the rest should be your job, right? So for the permutation GA, you need to use, because right now we have a good skeleton for generic GA solver. So what you need to do is just override all this stuff. But you need to prepare particular information about your crossover. So definitely you have your own crossover enumeration, mutation enumeration. So later on, once you create an object, then in the property grid, this kind of information can be pop up for the user to change the selection. Okay, so I think that's it. Is there any question about this implementation? So if you are capable, and I think you can still carry on the implementation of real number encoded to the GA. So basically, they should be exactly the same. But you should use an extra information about the user provided lower bound and upper bound. For example, to do mutation or to do the initialization. For example, if you overwrite the initial population, right? So what will you do for int as stuff as smaller than number of gym plus plus, right? So since it's a real number, right? So everyone should have its lower bound specified. So how can you initialize each one? So you initialize each gym j start from 0 j. Oh, excuse me, sorry. For int p equals 0, p smaller than population size, p plus plus. So that is for real number encoded GA. So what should be initialized with randomizer, right? Next double. So that will times upper bound ice gym minus lower bound. Ice gyms. So we know gym I have upper bound and lower bound. So we get the range first and then times up it with a random variable whose value between 0 up to 1.0. And then we add up lower bound. So it is really straightforward. Once you know the lower bound and upper bound, so we can initialize a chromosome P, right? The gene is S gene. There. Alright, so similarly, you will use lower bound, upper bound probably for crossover operation and mutation operation because that is actual information required for real number encoded GA and also integer number encoded GA. Later on, if you like, you can implement that integer number encoded GA too. So appreciate, our structure, our genetic GA structure. So different kind of encoding GA can easily be implemented. That is the beauty of object-oriented technology. We have with so-called extendability. So it will be very easy if you do object-oriented programming. It will be very easy to extend your current functionality to incorporate different kind of modeling or computation requirement. All right, so I think that will be all for today's lab. So for this assignment, what you need to accomplish is the genetic is a permutation tree. And as you can see, even though we are familiar with the operation, handwriting operation about this different kind of crossover operation, it takes time to design computational procedure to carry out the computation, the crossover computation correctly. So definitely you will spend a lot of time debugging the result, whether the result meet the permutation requirement or not. All right, so I hope that you will design the logic by yourself and implement that and debug that. All right, so once you finish an operation, definitely your programming capability will be elevated. Don't just clone others' work, okay? And the one I have shown up right here is an example for you to follow. And as you can see, it's kind of complicated, right? Array. All right, so forget about the implementation. Individual-wise, you can always use some simplified notation to help you understand. But the idea is behind that. So I need to create a mapping array. So later on for the algorithm to use. Okay, so then probably there is some bug there. I don't know. I cannot remember exactly. So just if you don't have any particular design of the PMXO operator, you can do that. You can implement that. Or probably you may Google it. I don't know. Maybe in the internet, certain guys has generate a more concise algorithm better than this one. It's okay. I mean, once you understand the computation procedure, but you need to write it down in pseudocode to let the reader know what exactly operation has been done within this algorithm. So let the user identify whether this algorithm can generate correct solution or not. All right, so if you don't have any question, we will end up right here. So if you still have any question, I will remain here. You can come up to here to ask me. Okay, so that's it for today. And then remember that before you leave, you need to hand in the answer sheet of today's quiz. All right. 好，稍等一下，我先把它刻起来。